Nuclear magnetic resonance spectroscopy, also known as NMR. This is a method used to determine the structures of molecules and the exact position of functional groups in certain compounds. Now, there are two types of NMR that we're going to meet. The first one is the more straightforward one. It's the Carbon-13 NMR. And then the second one is what we call proton NMR. That one's slightly more complex. I'm obviously going to talk in great detail about what various NMRs mean and how we actually use them. But just to give you some context, you'll be provided with something like this, which in this case is a Carbon-13 NMR. On the y-axis, it shows the energy absorbed, and on the x-axis, it shows the chemical shift. And then there'll be a variety of peaks. And then based on what I'm about to teach you, you'll be able to work out the structure of a compound. This is incredibly important, this TMS, because it has a shift of 0 by definition. And I'm going to tell you now what TMS is. Just note here that the x-axis goes from right to left. So in effect, here's your origin. So what is TMS? Well, it stands for tetramethylsilane, and this is our NMR reference molecule. So every other compound we look at is basically compared to TMS. What is the structure of TMS? What we're going to do is compare the chemical shift of other compounds with TMS. And so, by definition, the chemical shift of the carbons and hydrogens in TMS is 0. And why do we use TMS as our reference molecule? First of all, it's because all the carbons and hydrogens are in the same environment. Look, it's a totally symmetrical molecule. Other useful properties, it's inert, so unreactive. It's non-toxic. And lastly, it's easy to remove from the sample. So TMS is our reference molecule, and all the other compounds we're going to study are going to show a variety of chemical shift, which we'll compare against TMS, which by definition has 0 chemical shift. And these are the reasons here why we use TMS as our reference molecule. I just want to write this statement and then we'll look more closely at some examples. So NMR spectra give, you'll see me talk about this all the time, the chemical shift measured in parts per million of atoms in different environments compared to that of reference molecule TMS. So you'll be using this table all the time in your data booklet. This shows the type of carbon on the left-hand side, and then over here we have the chemical shift given in parts per million. And we're going to use this table in order to interpret the 13 carbon NMR spectra. One thing to point out is, as I've said here in my revision guide, the table below is given in your data booklet, and it gives the expected chemical shifts for carbons in different environments. A carbon's environment is based on its proximity to other atoms, and only symmetrical carbons will be in the same environment as each other. This is very important. So as soon as you have a symmetrical compound, that will reduce the number of carbon environments more than you might think. The closer a carbon is to an electronegative atom, such as oxygen, nitrogen, fluorine, or a double bond, the greater the chemical shift. So as I already told you, this is in effect our origin. Here's our TMS, our reference molecule. These are the peaks on our NMR. So obviously the further along the x-axis they are in this direction, the greater the chemical shift. So we would expect any peaks that occur down this end to be either close to a double bond or close to a highly electronegative element. So now it's time to apply everything that I've just gone through. So here we have propan-1-ol, and I'm just going to talk you through how this NMR basically informs you of the structure of propan-1-ol, because often in the exam you'll be given something like the molecular formula C3H8O, and obviously you'll have no idea what homologous series this compound belongs to. However, through the NMR spectra, you'll be able to work out the various carbon environments, which will enable you to determine that it's propan-1-ol. But to begin with, we've got our structure here. So here's TMS, which has a chemical shift of 0. This first peak here has the lowest of the chemical shifts compared with the other peaks. Why? Because it's closest to TMS. And so that green peak here is responsible for the CH3 here. Then as we move along to the central carbon, it's getting closer to a highly electronegative element, so we're going to see slightly more of a shift. And then lastly, this carbon here is obviously very close to the oxygen, so we see a large chemical shift, and we'll actually be able to cross-reference these peaks with this table in the data booklet. So for example, 60 here, as you can see, yes, it falls into this range here, and therefore it's telling us that it's either going to be an alcohol, ether or ester. In this case, it's going to be an alcohol because it fits our molecular formula of C3H8O. So you can cross-reference all of these peaks with the data booklet. Obviously, there are some overlapping ranges, so it will be a little bit of trial and error to work out where the functional groups lie. Now, this molecule, propan-1-ol, has 3 carbon environments, and therefore you can see 3 peaks. Do notice that with 13 carbon NMR, the height of the peaks is irrelevant. When we look at proton NMR, the height of the peaks will become far more significant. Now we're going to take a second example, this time with a symmetrical molecule. So we have cyclohexane 1,2-diol. So let's just work out what we would expect to see. Okay, here is my line of symmetry here. And as soon as you have a line of symmetry, it means that matching carbons such as these two are in the same environment, so they'll show up as only one peak. So that's one environment. Here's our second environment, here's our third, and that's due to the symmetry. So we would expect to see 3 peaks, which we do. Then we have the alcohol functional group here. Remember, oxygen's highly electronegative, so the carbons next to the oxygen would have the greatest chemical shift, and as we know, that means they'd be situated furthest to the left. I'm just bringing in that table again. So just to look, this is around 75, this peak. Sure enough, it corresponds to being an alcohol. So as always, you can line up the data table with what's going on here in terms of the peaks. Taking yet another example. So here we have a line of symmetry which exists just here. So if we count the number of carbon environments, it's not 1, 2, 3, 4, 5, 6. Instead, due to this line of symmetry, these 2 carbons exist in 1 carbon environment. So that would produce 1 peak, 2 peaks, 3 peaks, 4 peaks. 1, 2, 3, 4. There's our reference molecule again. Here's our highly electronegative nitrogen, so you'd see more chemical shift at the carbons closest to the nitrogen. Now this compound here has no symmetry whatsoever, so we have a huge number of carbon environments, 1, 2, 3, 4, 5, 6. Here's your double bond producing a huge chemical shift, so these peaks exist very far down this axis. And this carbon here next to the oxygen exhibits a large chemical shift. Now let's have a look at another type of way they could ask you about this. So isomers A and B have the molecular formula C4H11N, and they're both secondary amines. In their 13 carbon NMR spectra, A has 2 peaks, B has 3, deduce their structures. So crucially, we've been told that these compounds are secondary amines. Remember, amines look like this. If you have a primary amine, one of those hydrogens is replaced with an R group. And if you have a secondary amine, it means that a second of these hydrogens is replaced with an R group. So in terms of their structures, that's a very good starting point, because we now need to work out the layout or arrangement of all these carbons. So the next thing to look at is the fact that we've been told that A has 2 peaks, which means it has 2 carbon environments. So to look at A, we need to obey this molecular formula. We know it needs to be a secondary amine. We know that it has 2 carbon environments, but look, we've got to try and fit 4 carbons in. So those 4 carbons have to fit in 2 carbon environments, which means we must have a symmetrical compound. So actually, if you look at our final answer, yes, we have our secondary amine, and yes, the molecule is symmetrical, and therefore those 2 carbons there are part of one environment. These 2 are part of a second environment, so we would expect 2 peaks on our NMR. Now looking at B, where we know we have 3 carbon environments. Again, there's a bit of trial and error here, but we do have the basic structure of knowing that it's a secondary amine. So the way in which we can fit 4 carbons into 3 environments is making sure there's a little bit of symmetry here so that these 2 methyl groups are in the same environment, allowing us to have our 3 peaks on the NMR. How many peaks are there in the 13 carbon NMR spectrum of 1,4-dimethylbenzene? So what you want to do first of all is draw the structural formula. I'm going to draw the skeletal formula. There's my benzene ring. There's carbon number 1, carbon number 4. That's how you draw the skeletal formula of 1,4-dimethylbenzene. There's no need to write CH3 here. Now, because we're being asked how many peaks, that's really how many carbon environments. So I'll use my highlighter to demonstrate them. There's 1 carbon environment. It's symmetrical with this one, so that's the same carbon environment. That's a 2nd carbon environment. And then again, because the compound is symmetrical, those 4 carbons are all part of the same environment. How many different colours have I used here? 3, so the answer here is C. How many peaks does this compound have in its 13 carbon spectrum? Let's colour code again. 1 carbon environment, 2, 3, 4, 5, 6, 7, 8. It's not a trick question, the answer here is 8. NMR and infrared spectroscopy are used in organic chemistry to distinguish between compounds and to identify them. Give the skeletal formula of the compound that is used as the standard when recording a 13 carbon NMR spectrum. We need to draw the skeletal structure of tetramethylsilane. So we just need that central silicon atom, and then we show the 4 methyl groups simply by doing that. 4 isomers of C6H12O2, PQRNS as shown in figure 1 were analysed by our NMR spectrometry. 3 of these isomers as shown in figure 2. Use table C in the data booklet to help you identify which isomer produces each spectrum. So I've just grabbed that table from the data booklet, just popped it in here so we can see it more easily. So in effect, here are 3 spectra, and we have to decide which of these isomers produced each spectra. So in all honesty, I think the easiest way of doing this is first of all going through each of these structures and working out how many carbon environments we have, and therefore how many peaks we'd expect to see on the infrared spectra. So there's 1 carbon environment, 2, 3, 4, 5, 6. So we'd expect to see 6 peaks here. What about this isomer? Just be careful here. These 2 methyl groups are part of the same carbon environment. 2nd, 3rd, 4th, 5th. 5 peaks for Q. Let's look at the number of carbon environments and therefore peaks for R. So these will all be part of the same environment. So that's 4 peaks. And then lastly, 1, 2, 3, 4 peaks. So now we're ready to look at our NMR. Just count the number of peaks. 4 peaks. 4 peaks. 1, 2, 3, 4, 5. 5 peaks. So that 5 peak one will be easy. Where did I write 5? Just here next to Q. So immediately we write Q here. This is obviously trickier because we have 4 peaks for both. 2 options here with 4 peaks R and S. So now we need to try and differentiate between the 2. Now looking at the major differences, it's here you've got a carboxylic acid versus an ester down here. Let's just have a look at this ester. Now here, because that carbon environment here is next to an oxygen, you'd expect to see more of a shift. So let's just have a look down here, and sure enough, there's the largest shift here compared with here. So that means that this particular NMR belongs to our ester, which was S. And therefore, by process of elimination, that means that that must be R. K and L are cyclic compounds with this molecular formula. Both have 4 peaks in their NMR spectra. K is a ketone, L is an aldehyde. So higher up in the question, we're being asked to determine their structures. Loads of information here. So K is a ketone. So obviously we'll expect this functional group. On a ketone, L is an aldehyde, CHO. We've been told that they're cyclic compounds made up of 6 carbons. So let's start with our ketone. And I'm just going to explain to you why this is the structure of K, because there's 1 carbon environment. It's symmetrical, so there's the 2nd, 3rd, and 4th. So therefore we'd expect 4 peaks. So just to double check, is K first of all obeying the molecular formula C6H10O? Sure enough, 1, 2, 3, 4, 5, 6 carbons, 2, 4, 6, 8, 10 hydrogens, and there's our O. Is it a cyclic compound? Sure enough, yes it is. And then do we have 4 peaks represented by 4 different carbon environments? Yes, we do. What about our aldehyde L? This will take practice, but I'm just going to explain to you why this is correct. So we have our aldehyde functional group. Let's count the carbon environments. 1, 2, 3, and 4. So yeah, another 4 peaks. And we know that it's cyclic again. When the molecular formula of a compound is known, spectroscopic and other analytical techniques can be used to distinguish between possible structural isomers. Draw 1 possible structure for each of the compounds described in parts A to D. So we're going to go in straight here. Compounds F and G have the molecular formula of this. They're both dinitrobenzenes. F has 2 peaks, G has 3 peaks. So the fact that they're dinitrobenzenes means that we're going to expect to see a benzene ring. The nitro bit means we're going to have an NO2. So let's start with F. We know that it has 2 peaks, so that's 2 carbon environments. But we've got to accommodate 6 carbons. So here's my benzene ring. 2 carbon environments needing to accommodate 6 carbons means we'll need a great deal of symmetry here. So I'm just going to draw a dotted line here and add my NO2s. Right there, marking off the carbon environments then. There's obviously 1, and then because of the symmetry, those 4 carbons belong to the same carbon environment, so I'm happy that that's my structure for F. What about my structure for G, which I know has 3 peaks, so 3 carbon environments. There's my benzene ring. Let's add a dotted line just to show you how we're working out these carbon environments. They're both in the same carbon environment, and then a 3rd carbon environment. So yeah, 3 peaks.